If you're watching this on a phone or a tablet or a computer, you're basically looking at billions of transistors, all firing away, working together just to light up your screen. It's kind of mind-blowing. So how does this tiny, completely invisible switch pull off such a massive job? Well, let's break it down.
And honestly, it's almost impossible to overstate their impact. These little things are the absolute bedrock of all modern electronics. They make everything, from your smartphone to the rockets that go to space, possible. They are literally the invisible switches that run our entire digital world. All right, so here's our game plan. We're going to start with the absolute basics, what a transistor even is. Then we'll meet its two main families. After that, we'll see how to actually use one in a simple circuit, which is pretty cool. Then we'll explore its other superpower, amplification. And finally, we're going to peek under the hood at the incredible semiconductor science that makes the whole thing possible.
So let's get right to it. At its very core, what is a transistor? Well, at its heart, it's a really, really elegant solution to an old problem. How do you build a better switch?
Okay, think about a regular light switch on your wall. A transistor does the exact same job. It turns a current on and off. But, and this is the game changer, it does it with absolutely no moving parts. It's what we call a solid-state device. It's just a solid chunk of material with no gears or levers, and instead of you physically flipping it, it's controlled by a tiny electrical signal. That's what makes it silent, super reliable, and unbelievably fast.
And this is where you really see the genius of the transistor, especially when you put it up against the old tech it replaced, the relay. Now, a relay is also an electrical switch, but it's big, clunky, and mechanical. It needs a good chunk of power, maybe around 100 milliamps just to click on. A transistor? It can do the same job with less than 10. But the speed? I mean, it's not even a fair fight. A relay is slow because metal parts have to physically move. A transistor, with no moving parts, can switch on and off millions of times a second. This is the leap that let us shrink computers from the size of a room down to something you can put in your pocket.
Okay, so while the basic idea is simple, it turns out not all transistors are created equal. They pretty much fall into two main families, and each one has its own special talents.
First up, you've got the BJT, or bipolar junction transistor. This is kind of the classic workhorse you'll find in tons of hobby projects. It's controlled by a small amount of current. Then you have the MOSFET, or field effect transistor. This one's controlled by voltage, which makes it way more efficient and a lot faster. For the rest of this explainer, we're mostly going to focus on the BJT, just because its principles are a fantastic starting point for understanding how all transistors work.
So every BJT has 3 pins, or terminals. Just think of the collector and the emitter as the two ends of our switch. Current wants to flow between them. The third pin, the base, well, that's the control knob. The signal you send to the base is what decides if that switch is on or off. Simple as that.
Now, these BJTs come in 2 flavors, NPN and PMP. For what we're doing, the main difference is just which way the current flows and how you turn them on. And you can spot the difference instantly just by looking at the little arrow on the symbol. On an NPN, the arrow points out. On a PMP, it points in. And hey, here's an easy way to remember it. The mnemonic for NPN is not pointing in. Works every time.
Okay, theory is great and all, but let's see how this thing actually works in the real world. We're going to put together a super simple circuit just to turn on an LED. Here is the golden rule you have to remember. To get an NPN transistor to turn on, to let that current flow from the collector to the emitter, its base needs to be about 0.7 volts higher than its emitter. That 0.7 volt difference, it's like the key that unlocks the gate. So, to get that perfect 0.7 volts and just a tiny little control current, we use a resistor. Let's say we have a 9-volt battery. We know the transistor is going to use up 0.7 volts, which leaves 8.3 volts for our resistor. Then we decide we want a really small base current, like 0.1 milliamps. Now we can use a super basic rule called Ohm's law. Don't worry, it's easy. It just says resistance equals voltage divided by current. You do that quick bit of math, and boom, it tells you the exact resistor you need for perfect control.
Okay, but I know what you might be thinking. This seems like a lot of trouble just to turn on a little LED, right? Why not just hook it straight up to the battery?
Ah, and this is the real magic of the transistor. You use a tiny, tiny current at the base to control a much, much larger current flowing through the main circuit. Think about a microcontroller, like an Arduino. The little pins on that board can only push out a tiny bit of current, not nearly enough to run a big motor or a super bright light. But it can easily provide that tiny base current the transistor needs. So the transistor acts like a force multiplier for electricity. The Arduino whispers and the transistor shouts.
But wait, there's more. A transistor isn't just a simple on or off switch. It has a second, equally amazing ability. It can amplify things.
This part always feels a bit like magic, doesn't it? How can something that's basically just on or off also make a signal stronger? You know, like turning up the volume on a speaker?
Well, the secret is a special state called the active region. Instead of an on-off switch, think of it more like a dimmer switch. In this state, the transistor isn't fully on or fully off. It's somewhere in between. And here's the really cool part. Any tiny little change you make to the small base current causes a proportionally huge change in the main collector current. That amplification factor, that ratio, that's what engineers call gain.
We can actually see this on a graph called a load line. All this line really shows is every possible combination of current and voltage for our transistor circuit. At one end of the line, you have cutoff, which is just off. At the other end, you have saturation, which is fully on. But for a nice, clean amplification, we want to hang out right in the middle of that line, the sweet spot. That gives our signal plenty of room to swing up and down without getting cut off. And this process, setting up that perfect middle operating point, has a name. It's called biasing. It's kind of like tuning a guitar before you play. By picking just the right resistors, we set a default idling state for the transistor, right in the center of that active region. That way, when our small signal comes in, it can be amplified cleanly without getting all clipped and distorted.
So, how on earth is any of this, the switching, the amplifying, even possible inside a solid piece of rock? Well, the answer lies deep in the science of semiconductors.
The key to the whole thing is a process called doping. You see, pure silicon is actually not a very good conductor of electricity. But if we intentionally sprinkle in tiny, precise amounts of other elements, what we call impurities, we can fundamentally change its electrical personality.
And this doping creates two different types of material. If we add an impurity that has an extra electron to spare, we get what's called N-type material for negative. But if we use an impurity that's missing an electron, it creates a hole, basically a spot where an electron should be. And that's called P-type material for positive. A BJT transistor is really just a sandwich of these materials, layered as either NPN or PNP.
So what's actually happening here? Well, in pure silicon, the electrons are pretty much locked in place. They need a huge push of energy to jump across something called the band gap and start flowing as current. Doping is like building a stepping stone right in the middle of that gap. It cleverly creates these new energy levels that make it drastically easier for electrons to get moving. And that is the secret sauce. That tiny signal at the base just gives the electrons enough of a nudge to start a massive flow across this new, easier path from the collector to the emitter.
From the very first giant computers to the device you're probably holding right now, the story of the transistor has been all about mastering the control of electricity on a smaller and smaller scale. It really is the switch that changed everything. And it leaves you with a pretty cool question to think about. If this incredible device built our digital world by controlling electricity, what will the next great transistor control?